We're going to start with association tests, and I'm going to use a classical example, the lady tasting tea example. And this is a real experiment that was performed by R. Fisher about 100 years ago now, almost 100 years ago. There was this lady that he worked with, or that he knew, that claimed that if you gave her a cup of tea with milk, she could tell if the milk was poured before or after the tea. And I imagine that Fisher did not believe her and wanted to test if she could actually do it. So, he actually did this experiment where he gave her pairs of cups, 4 pairs. Each time the tea was poured before, and the second time the tea was poured after. And the lady had to try and say which of the two it was that was poured after. So let's say she got 3 out of 4 correct, which is more than half. Do we believe that she has a special ability? So that's something, that question we can try to answer with statistical inference. And the specific topic that we're going to cover is hypothesis testing. So what we're going to try to do is we're going to quantify the answers to the question, could this happen by chance? So the way we do this is if the lady is just guessing, then we're going to try to find out what is the chance that she gets 3 or more correct. Once we figure that out, we'll have a better idea if she actually has this special ability or not. So when we use statistic and its probability distribution, a summary of the data and its probability distribution to answer this question, that's when we call this hypothesis test. Sometimes we just say test for short. Now, we can think of this particular example of the lady tasting tea as picking 4 balls out of an urn with 4 green balls that represent the correct answers and 4 red balls that represent the incorrect answer. So she's just guessing, so this is what we're going to be doing. It will be equivalent to this. And once we have this set up, then it's relatively easy to figure out what these probabilities are under the null hypothesis. That's a term we're defining now. The null hypothesis is that the lady is just guessing, and that each ball has the same chance of being picked. So what is the probability of picking 3? I'm not going to go into the details of combinatorics here, but you can easily find information on that. But you can basically figure out all the combinations that give you 3 correct answers by chance. And the formula is going to be 4 choose 3 times 4 choose 1 divided by 8 choose 4, which is 16 out of 70. And then the probability of picking all correct is 4 choose 4 times 4 choose 0, which is 1, divided by 8 choose 4. So it's 1 out of 70. So the chances of observing 3 or something more extreme than 3, which is just 4 in this case, under the null hypothesis is 0.24. So that's not that impressive. It happens by chance a quarter of the time. And this probability that I just described is what we refer to as a p-value. Association tests in genetics use similar tests to this one that we just performed. In the previous example, we used the hypergeometric distribution to compute probabilities. In association tests, we're going to use a slightly different test, but it's actually similar, at least in flavor. So the Manhattan plot we showed at the beginning, it typically has, on the y-axis, it's showing you the -10 log p-value. Right? So essentially, it's showing you the p-value. They take the negative log so that it goes up when the p-value is small. So to compute this p-value, what do we do? In this case, we have several individuals. Some of them have disease, others don't. And we observe that a larger proportion of the individuals that are homozygous for a minor allele, so they have a specific genetic background in a specific location, have the disease compared to the rest. So we see this. We see a bigger proportion. Right? So we say, maybe this is a gene or the genomic location that's associated with this disease. But again, we ask, would we see this again if we picked another n individuals? That's what inference does. So here's an example. You can see an example of an outcome that we could get. So we obtain a random sample of the population, and we have 2 groups, the minor allele group, that's on the second row, and the rest on the first row. And you can see that we have 20 out of the 200 in the first group have the disease, and 10 out of 50 in the second one have the disease. So we see that there's 20% in one group, 10% in the other, so it's twice as much on the second group. So is this enough to say, yeah, this is a location, this is a SNP, this is a gene that is associated with this disease? So again, we're going to do a test, a statistical test, to see if this could happen just by chance. So what we're going to do now is we're going to assume, we're going to pose a null hypothesis that there's 200 individuals and 50 individuals in each group. Now we're going to assume that each one was assigned disease or not by chance, so it has nothing to do with which group they're in. If we do that, then we can compute the expected number of individuals in each cell. So the first thing we're going to do is we're going to estimate that probability from the data. So we're going to ignore genotype, and we're going to compute the proportion of individuals that have the disease, which in this case is 12%. And now we can create a table with the expectations in it. And then we're going to ask, how likely is it to see a table like as different from the expected one by chance under this null hypothesis that we're just assigning the disease at random? Now the mathematics behind this is a little bit complicated. We perform what is called a chi-square test, where you take the differences between the expected and observed counts, we square them, we divide them by the expect squared, and then we can prove that has an asymptotic distribution of a chi-square. I'm not going to go into the details of how that's done, but in the labs we're going to see how you do it in R. Now in this particular case, it turns out that the p-value is not very big. It's only like 8%. So again, we're shown that even though we saw a difference, it was actually a difference that is not that unlikely. I mean, 8% is not a small number, but it's also not a number that is smaller than what we usually require in journals, which is 0.05 or 0.01. Now, if the table, one important note I want to make is that there is not a one-to-one relationship between the odds ratio, between the ratio of the proportion, the difference in proportions, and the p-value. This is because the more data you have, the harder it's going to be, more unlikely to see differences, big differences as big as the one we saw by chance. So I just added another table here so you can see if I multiply everything by 10, now the p-value drops below 10 to the minus 8. So the more data, the variability due to randomness decreases with respect to the real differences. So that's something that it's important that you're aware of, that sometimes you can have a very small p-value and not necessarily a big difference in proportion.